Am I audible?
Yes, sir.
Okay, now we can start.
Yes, sir.
है ना? Okay, so in last class we have studied the design of the continuous decanter and centrifuge decanter. Okay, so what I am going to do, I will give you some numericals related to the continuous decanter and the centrifuge decanter as a assignment problems. Okay, so you have to solve this problem. If you have any confusion or any doubt, you can, then we will discuss the problem in class. Okay, so first you have to try to solve the problems related to the barometric related to the barometric equations, then YouTube manometers, and continuous and centrifuge decanter. So these four theories I have covered till now, and you have to use these theories to solve that problems. Okay, so I will give you the assignments by today or tomorrow. Okay,
Okay,
now
sir.
we will come to the next chapter, that is related to the fluid dynamics. Okay, so fluid dynamics means now we will study the behavior of the flowing fluid. Okay, so some of the part you have already studied in the transport phenomena. In the fluid mechanics we will extend that part. Okay, so today we will revise some of the topics, and then we will extend the part of the fluid dynamics. Okay, so fluid dynamics basically is the part of momentum transport which you have already studied in the transport phenomena subject. So we will quickly revise some of the topics which will also covered in the fluid mechanics. Then we will go for the next part. Okay, so the some of the basic concept of the fluid dynamics covers like the no slip boundary conditions. So what is the no slip boundary condition? Anyone? What is the no slip boundary condition?
So
सर
that
shear force इक्वल होना चाहिए बॉन्ड.
हाँ, है ना? So basically the at liquid solid interface, the velocity of the liquid layer is equivalent to the velocity of the solid layer. That is called the no slip boundary condition. Okay, so at liquid solid interface, the velocity of the liquid layer and velocity of the solid layer is same. If here v equal to v naught, the this layer fluid layer also has the v equal to v naught. Okay, so that is the no slip boundary condition. So the fluid in contact with the solid surface has the same velocity as the solid surface. This is the no slip boundary condition. Okay, now second point which we important in the fluid dynamics is the Newton's law of viscosity. So I have already explained you the Newton's law of viscosity in very detail in the transport phenomena. So I'm just going to I will not explain the basic concept of the Newton's law of viscosity. I will just come to the final equation. Okay. So what the Newton's law of viscosity tells you, that shear stress tau xy is equivalent to minus mu dvy by dx. This is the Newton's law of viscosity. Okay, so shear stress is proportional to the shear rate, and when the proportionality sign removes, a constant curve that is called the viscosity. Basically, viscosity is the hindrance to flow, and this is the resistance to flow, viscosity. Okay, and the viscosity, well, the units of viscosity is poise, centipoise, or Pascal second. Okay, so these are the units of the viscosity. So this is the viscosity of fluid. Okay, so the unit of the viscosity is kg per meter second, or called the Pascal second. The CGS unit is gram per centimeter second, which is also known as poise, or poise can represented by the capital P. So the 1 poise equal to 0.1 kg per meter second, or 0.1 Pascal second. Okay, sometime you also have the unit centipoise. So 1 centipoise equal to 0.01 poise. Okay, so the air velocity at 25 degrees Celsius, why the centipoise is very important? Because water velocity is around 1 centipoise at 25 degrees Celsius. Okay, so the air viscosity is at 25 degrees Celsius, viscosity of air at 25 degrees Celsius equivalent to 0.018 centipoise. The viscosity of water at 25 degrees Celsius equivalent to 1 centipoise, and viscosity of some of the melt or some of the paste which used in the chemical industry, like polymer melts or some type of thick paste, है ना? So the polymer melt or pastes used in chemical industry has the viscosity. This have the viscosity in the range of 1000 centipoise to 1000 to 1 lakh centipoise. Okay, so you can see that the dimension of viscosity is huge. If you are saying the viscosity of air or viscosity of gases, it is 0.01 centipoise. For water, it is 1 centipoise, and so for some of the chemical, it is 1000, even 1 lakh centipoise. So the dimension where you are studying the viscosity, that is huge. Okay, so it will affect the related physics, है ना? So when you are solving some problem, so if the material for which you are solving the problem is viscosity is very less, then the physics will be different than the physics which is used to solve the problem where viscosity is very high. Okay, so it will affect the solutions. That's why fluid mechanics is very complicated, है ना? Because you are working with the properties there, where the range of the property of the value of magnitude of the property is very large, है ना? The range of the magnitude of the property is very large. Okay, so this is one of the basic characteristic of the fluid. Okay, now then I have already covered the Reynolds experiment in the laboratory class, so I am not repeating that. Then you have the internal and external flow. So what is the internal and external flow? Basically, when a solid body is surrounded by the fluid, that is called the external flow. Okay, if solid body is surrounded by a flowing fluid, that is called the external flow. And second, if the flowing fluid is surrounded by the solid body or solid surfaces, that is called the internal flow. Okay, suppose flow inside the pipeline, that is the internal flow. Okay, so basically external and internal both flows are important. Okay, they have their own application, and the physics also differs in the internal and external flows. How the physics differs? When you have the external flow, when a body is surrounded by a flowing fluid, then the fluid will exert the force on the body. Okay, so this flowing fluid will exert a force on the body, so that is called the drag force, है ना? So then you have to study the drag force. So sometimes the body will move and sometimes body will not move. Okay, sometimes body will move in the opposite direction. So suppose you are calculating how much drag is exerted by the winds on a aeroplane. Okay, on a flying aeroplane. So you have to calculate how much force is exerted by the different type of the force exerted by the air on the flying airplane. So at that time, the plane is also moving in the opposite direction of the fluid. Okay, sometimes you are calculating how the force is exerted on the winds or the very cyclone winds on a bridge or on a civil structure. So at that time, you are calculating how the moving fluids will exert the force on a stationary structure like a bridge or like a building and a multi-story building. So both are the different type of problem. In one problem, solid body is moving against the wind, against the fluid. In other problem, the fluid is moving against a stationary body. Sometimes both are moving and in the one direction or opposite direction. Suppose you are calculating what is the critical velocity of the particle in a fluid. Okay, the critical velocity is a constant velocity from which a particle is moving inside a fluid due to the influence of gravity. And a critical velocity is generally how the particle is moving in downward direction due to with a constant velocity due to the influence of the gravity. So that is the critical velocity. So how the particle will settling down, that have the specific application when you calculate the settling velocity or when you calculate how the solid liquid separation occur in industry. You know, sometimes you have to separate it out the solid, or sometimes you have to calculate even that also use when you calculate the size of the solid body, solid particles. So by calculating by predicting the density of the material and the settling velocity, you can predict the size of the particle also. Okay, that you will study in the fluid particle mechanics, in the fluid particle mechanics subject or mechanical operation subject. Okay, so basically when external flows have their own application and their own physics, but in chemical industry most of the problem is related to the internal flow. So in the internal flow, the solid body will exert the shear means friction, shear force on the flowing fluid. So the solid surface which surrounded the flowing fluid, that surface will exert the force on the fluid. In the external flow, generally fluid will exert the force on the solid body, that is called the drag force. Here, the solid body will exert the force on the fluid, that is called the shear force. Okay, so in one chapter we will study the drag force, in another chapter we will study the shear force. Okay, so we will start with the shear force because the internal flows are more important in the chemical industry. In chemical industry, most of the time fluid mechanism is applied for transporting the fluid from one part of the unit to the other part of the unit, or sometime for transporting the raw material from the field or from the mines to the industry, and for transporting the product from the industry to the end applications, like petroleum. So you have to transport the petroleum crude oil from the some oil field from the Arabian countries to the refinery in Mathura or Panipat. Then you have to transport that petrol or diesel, the product from the refinery to the petrol pump. Okay, so that transportation occur inside the pipelines. Okay, so for you have to design the pipeline, you have to simulate how much pressure drop is occurring in the pipeline, how much power is which type of pumps are required, how much big pumps are required for transporting the fluid. Okay, so these all things we will study in the internal flow. Okay, and when we study the how the particle will flow inside a fluid, or how the force is exerted on a moving body, and sometimes for mechanical engineers, external flow and internal flow both are equally important. For chemical engineers, generally internal flows are more important than the external flow. Okay, in chemical engineering, generally we study the more about the internal flow than the external flow. But for mechanical engineers, external flows are also equally important because they have to design the transportation vehicles. Okay, suppose you are designing a car. If the geometry of car is not very very unique, then the drag will be very high. Okay, if the drag will be very high, your fuel consumption will be increased. Okay, so you have to make a streamline flow. Streamline flow is a type of body geometry where the drag force will be minimized. Okay, so that we will also study how the drag will be minimized. External flow is used in the chemical industry, especially when you are dealing with the solid liquid separation. Okay, sometimes we use the solid particle as a catalyst. So how to use that we will discuss. That is called the fluidization of the particles, of fluidization of the catalyst. So how we separate it out, how we mix the solid catalyst in the flowing fluid, and sometimes how we separated out the solid particles from the flowing fluid. So that will be the part of the chemical industry where we use the external flow. Okay, otherwise mostly we will study the internal flow. Okay, so these are the external and internal flows. Then the next part is boundary layers. So developing and fully developed flow. So basically, what is the boundary layer? Basically, when a flowing fluid comes into contact with the solid boundary, due to the no solid boundary condition, the solid boundary will exert the friction force on the adjacent layer, and that layer will again drag the another layer. Okay, so there is a reason where the flow is influenced by the presence of solid boundary, that is called the boundary layer. Okay, so most of you are you was confused about the what is the difference between the boundary layer, fully developed, and developing flow. Okay, so I am clearing you in this subject. The boundary layer is the region where the fluid is influenced, the flow of the fluid is influenced by the solid boundary. Okay, so this is the solid surface, and at this region, suppose here your velocity, the fluid velocity is v infinite. So the where v infinite is less than zero, where the velocity is less than v infinite, there you have the boundary layer, because here in this region the velocity is the fluid velocity is influenced by the presence of solid surface. Okay, and where the velocity remains almost equal to the previous velocity, that is called the potential flow region. Potential flow means where the solid boundary will not affect the flow of the fluid, that is called the potential flow. Okay, so whenever you have the boundary layer, the fluid velocity will be influenced by the presence of a solid boundary. Okay, now in the boundary layer you have the two regions. One is the developing region, and second is the fully developed region. So what is the developing region and fully developed region? In developing region, the thickness of boundary layer is changed with the in the flow direction. Okay, so basically the boundary is developing. Developing means the thickness of the boundary layer is changing. So the if you are going from this point to this point, this is the parallel point. So here velocity is changing in the this direction. Suppose this is the x direction. So velocity is changing in the x direction, and velocity is of course changing in the y direction. So if the velocity is changing in the two direction, suppose v is the velocity that will changing in the x as well as y direction. So it is a developing region. Fully developed region is the region where velocity is changing only one direction. So here velocity will not change in this direction because boundary layer is fully developed. Velocity will change only in one direction, that is y direction. So when velocity is changing only one direction, that is perpendicular to the surface, when you move far away from the surface, your velocity will change. Okay, because the friction force will reduce, so velocity will change from this point to this point. So that is called the fully developed region, where velocity is changing only one direction. Okay, and beyond the boundary layer, velocity is equal at everywhere. And if you say what is the velocity difference in the potential flow region, their velocity is equal at every point. Why? Because that at that region there is no influence of the solid boundaries. Generally velocity changes due to the presence of solid boundary only. Okay, so this is for the external flow. In the internal flows, what's happened? Sometimes you have the internal flow where the fluid is surrounded by the solid bodies. Then the two boundary layers will merge to each other. Okay, so the region where boundary layers are developing, that is the developing boundary layer region, and region where the both boundary layers are merged to each other, there you have the fully developed. So in the fully developed region, again the velocity is only the function of one direction, that is the r direction. In this case here velocity is the function of r as well as z in the developing region. Okay, so in it is very difficult to solve any problem in the developing region. Why? Because in developing region you will have the two direction velocity which will depend upon two direction. So you will have the two shear rates, tau the velocity in the z direction, tau zr and tau zz. You have the two shear rates. You will have the partial derivative equations which are very difficult to solve. And when you write the equation, it will become the second order partial derivative equations. So second order partial derivative equations are very difficult to solve. If you compare the fully developed region, there you have the ordinary differential equations and a second order ordinary differential equation which you can solve by using the pen and paper. Okay, so comparatively this region is very small. If your diameter, the diameter versus length is, if length is very large, then the diameter of the pipeline or the flowing channel, diameter of the pipe is very small, the length is very large, this number is very small, is less than 50, then this region is generally negligible. this part is generally negligible than the actual fully developed reason. Okay, so either we will neglect the this part for solving the problem, or what we will do, we will change the length of the pipe. Suppose actual length of the pipe is L. So instead of using the L length, we will use a new length L dash. So why we are changing the length? So it will take care of the developing region effect. Okay. So instead of using that is called the effective length of the pipe. Okay. So instead of using the actual length, we will use the effective length. So when you use the effective length, that will take care of the change difference coming due to the developing region. Okay, because the equation we will use, the equation is for the fully developed region only. But because the pipeline, the actual condition have the developing region also, so we will change the length of the pipe. Okay, so that type of adjustment we can do whenever you solve the problem in the real scenario, so that your answer will be correct and it will not take a lot of efforts. Otherwise, you have to solve the second order, higher order partial derivative equation, which are very difficult to solve. You cannot solve using the pen and paper. You have to go for the numerical methods or the computational programs. Okay, so these are about the boundary layers in fully developed flow. Then we will come to the axioms, transport phenomena axiom. So I have already teach you in the class, the transport phenomena class. So I'm quickly repeating that, so you can remember that. Okay, first axiom is related to the mass is conserved. Which leads to the equation of continuity. Second equation is the momentum is conserved. Which leads to the equation of motion. Third is moment of momentum is conserved. Which leads to an important result that the second order stress tensor tau is a symmetric tensor, is symmetric. Symmetric means if you have tau ij, that should be equal to tau ji. That is the symmetric. That is the definition of the symmetric tensor. Okay. So generally, shear stress is a symmetric tensor. That is the result of the third axiom. First axiom told you the mass is conserved, which leads to the equation of continuity. And second axiom told you that momentum is conserved, which leads to the equation of motion. So I have already derived the equation of continuity in the momentum transport class. And in this subject, fluid mechanics, we will derive the equation of motion. Okay. So quickly, I'm repeating the derivation of equation of continuity, so you will remember that. Okay. So first we will derive the equation of continuity very fast. So axiom 1, mass is conserved. Okay. So for deriving the equation of continuity, first we will taking the approach. Basically, we are taking the approach where we are taking a rectangular shape control volume which is fixed in space. Okay. So this is the Cartesian coordinate system because we are using the rectangular shape control volume. So we will take the Cartesian coordinate system. X, Y, and Z are the coordinates of the Cartesian coordinate system. O is the origin of the Cartesian coordinate system. Then we are taking a rectangular shape control volume. So this is the rectangular shape control volume. Okay. So this is the x-axis, this is y-axis, this is z-axis. In x-axis, thickness of the control volume is delta x. In the y-axis, thickness of the control volume is delta y. In the z direction, the thickness of the control volume is delta z. Okay. And suppose the velocity of fluid is v. So this is the v is the vector, velocity is a vector quantity. So the component in the x-axis is the vx, the component in the y-axis is vy, and the component of the velocity in the z-axis is vz. Okay, so this point is, there are 2 points. So this point is x equal to 0, this point is x equal to x, this point is x equal to x plus delta x. Similarly, this point is y equal to y, and this point is y equal to y plus delta y. Similarly, here this point is z equal to z, and this point is z equal to z plus delta z. Okay, so that you have already done in the transport phenomena. Now we will write the mass is conserved. So suppose the rate of accumulation of mass in a time delta t. So first is the accumulation term. So let mass of the m and m plus delta m is the mass of the control volume at time t and t plus delta t respectively. Then you can say del m divided by del t should be equal to del by del t in bracket rho delta x. Basically density, mass equal to density multiplied by volume. So volume is delta x, delta y, delta z. This is the volume. So this is equation number 1. Now the change of mass of the system, that should be equal to inflow minus outflow. Okay. So if inflow is higher and outflow is lower, then you are starting to accumulating the mass inside the system, because mass cannot be destroyed and it cannot be generated. So the whatever the mass is changing of the system, that should be equal to the input minus output. Okay, that is the mass which is the mass of the system which is changing with the time. So I'm writing the same equation. Okay, so the second is net rate of change of mass. So net rate of change of mass, so that is equal to input minus output. Okay, so in each surface we have to write the equation. So the mass entering in the y surface, net rate of change or net rate of flow of mass in x direction, that is equal to velocity in x direction. First we will take the density multiply by velocity. So velocity is vx in the x direction, multiply the surface area. Surface area in the x direction is delta y delta z. Okay, so if you check what is the surface area in the x direction, that is equal to delta y multiplied by delta z. Okay, so material is entering at x equal to x, and it is leaving from x equal to x plus delta x. Similarly, we have to write for the other direction also. Net rate of flow of mass in y direction, that is equal to rho Vy delta x delta z at y equal to y minus rho Vy delta x delta z at y equal to y plus delta y. Similarly, you can write net rate of flow of mass in z direction, that is equal to rho Vz delta x delta y at z equal to z minus rho Vz delta x delta y at z equal to z plus del z. So suppose this is equation number 2, this is equation number 3, and this is equation number 4. So summation of equation 2, 3, and 4 should be equal to summation of 2 should be equal to equation number 1. Okay, so you can write 1 should be equal to 2 plus 3 plus 4. So del rho delta x delta y delta z by del t should be equal to equation number 2, that is rho Vx delta y delta z at x minus rho Vx delta y delta z at x equal to x plus delta x. Similarly, you can write the other terms. Okay, I am not writing the other terms. Okay, now divide the equation by volume of control volume, so you will get a point. So dividing equation by volume of the control volume, and takes the limit and take limit that take limit that delta x tends to 0, delta y tends to 0, and delta z tends to 0. Okay, so when you take this limit, you will end up with the equation del rho by del t equal to minus del rho x, rho vx divided by del x minus del rho vy by del y minus del rho vz by del z. Okay, now you can take this in one side, and if you write in the vector and tensor form, the equation will become del rho divided by del t plus del dot rho v equal to 0. Now you can again expand this equation. It will become rho del t plus rho del dot v plus v dot del rho equal to 0. Okay, now this term will become these two terms will become the substantial derivative. When you add these two terms, it will become d rho by dt, substantial derivative, plus rho del dot v equal to 0. Okay, so this is the final equation for the equation of continuity. Suppose you have the constant density. Suppose density is constant. Density is constant. Then the equation will become, these two terms will be cancelled out. Suppose density is constant, density will not change with time, density will not change with any position. So you will end up with equation rho del v equal to 0, or you can say, because density cannot be 0, that means del dot v equal to 0. If you write this equation for the Cartesian coordinate system, it will become, this will become dvx by dy del x plus del vy by del y plus del vz by del z equal to 0. So this is for the liquids. And because for liquids, generally density is constant. Okay, so this is the equation of continuity, derivation of equation of continuity. Now we will go for the second axiom, that is the momentum is conserved. Now second axiom, that is momentum is conserved. Okay, so this this axiom is basically the same as the Newton's second law for the solid bodies. Basically, Newton's second law is defined for the solid bodies. If you use the same law for the fluids, it will become the momentum is conserved. Okay, so basically what Newton's second law is telling, change in momentum is equal to the force. Okay, here also you have to add the force and add the momentum, that should be equal to. Okay, so here it is written as rate of accumulation of momentum in control volume in control volume, that should be equal to rate of momentum entering by convection minus rate of momentum leaving by convection plus summation of all applied forces. So what is the meaning of convection? Convection means momentum comes with the mass. Okay. So basically convection phenomena represent when the fluid flows from one point to other point. So it will take some energy, some momentum with it. That is called the convection. When you study the heat transfer, so in heat transfer, the fluid takes the heat energy or the thermal energy from the one point to the other point. That is called the convection. In mass transfer, in the fluid mechanics, when the fluid takes the momentum from one point to the other point, it is called the momentum convection. Okay, so because fluid is entering in the system, fluid is leaving from the system, so the momentum is increased or reduced due to the flow of the fluid. That is the one part. The other part is applied forces, है ना? So force due to the friction of the solid body, that is called the shear forces. So shear force sometimes written as this momentum, shear momentum. Okay, that is the another thing. Okay, you can write the shear force as a shear momentum, or you can represent it as a shear force. So that is although both okay. Okay, the second type of forces are the pressure force, gravity force that will apply, or the centrifugal force. Okay, so these are the forces which may apply on the flowing fluid. Now, the shear forces, that is due to the friction of the solid bodies. Then pressure force, pressure is a type of force applied on the fluid. Then you have the gravity force, which may occur, which may be occur on the body, so solid flowing fluid. Then you have the centrifugal force. Okay, so these are the different type of force applied on the flowing fluid. And you have the convection and the momentum convection, or convex the fluid entering due to the convection and fluid leaving from the convection. Okay, so these are the this is the theorem for the momentum is conserved. Now quickly I am telling about the different type of forces applied on the body that we have already covered in the momentum transport. There are two type of forces. First is the body force. Second is the surface force. So basically the body force is the force which is applied on the whole body. Okay, so it is a force. Body force depends upon the mass. And acts on the whole volume of the system. surface force generally do not depend upon the mass of the system. And generally depend upon the area or the surface of the specific surface of the system. You know? So it will depend upon the area and surface of the system. So example of body force is gravity and centrifugal force. So gravity and centrifugal force both act on the whole body and they depend upon the mass of the body. Okay, gravity and centrifugal force are the body force. Okay, and the example of the surface force is pressure force and shear force. Okay, so where how the pressure force will work? So basically pressure force is a compressive force. It will always work to the normal direction, the normal outward direction of the body. Okay. So suppose this is a surface. So it will always work if this is the flow direction. If this is the flow direction, so it will work in the compressive manner. Okay. It always work in the outward normal direction. Okay. So this is the surface force. Suppose this is the flow direction, then it will work in this direction. Okay, outward normal direction of the surface. Okay, so this is the pressure force. Then you have the shear force. So shear stress is a tensor quantity. So you have the 9 component of the shear force. If you're writing the shear stress in the Cartesian coordinate system, so there are the 9 component. So whenever you write the shear force as a shear stress, so the first component always represent the direction of surface and the second component they represent the direction of the force. So these are the forces applied on the x directed surface. These are the force applied on the y-directed surface. And these are the force applied on the z-directed surface. Okay, so suppose you are making a cube. So this is a big cube or rectangular control volume. So this is the x direction, this is the y direction, this is the z direction. So this is the x directed surface. So in the x directed surface, suppose you have the this tau. This is the direction of tau xx. This is the direction of tau xy. And this is the direction of tau xz. These all forces applied on the x directed surface in the different this all forces are the applied on the x directed surface. This is the y directed surface. So here you have the tau yy, then you have the tau yz, and here you have the tau yx. Okay, this is the z directed surface. So again you have here the tau zz, this is the tau zy, and this is the tau zx. So in this how you can represent the all different forces. Okay, so this is the direction of the forces in the Cartesian coordinate system. Okay, for different surfaces. Basically you have the 9 forces applied on the 6 different surfaces. Okay, so this is the basic of the second axiom. Now in the next class we will study the equation of motion, which is new, right? Since here you have already studied all the things in the momentum transport, but you have not derived the equation of the motion in the momentum transport, in the transport phenomena. So in the next class we will derive the equation of motion, then we will go to the Navier-Stokes equation, and then we will solve the see how the flow occurs in the different type of channels, flowing channels in the fluid mechanics. Okay, ठीक है, तो आज की क्लास यही खत्म करते हैं. आई थिंक वी हैव डन इनफ फॉर टुडेज क्लास. ठीक है,
ओके सर.
ओके सर.
ठीक है, नेक्स्ट क्लास कब है फिर? वेडनेसडे को.
यस सर.
ठीक है, तो वेडनेसडे को मिलते हैं. चलो.